Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion, where we will be finishing our discussion of Einstein's theory of relativity. I'm just going to tidy up a couple of loose ends that I left hanging at the end of my last lecture. You might remember, during the last lecture, we talked about the relationship between energy and momentum that is consistent with Einstein's theory of relativity, namely, that the energy of an object squared is equal to the sum of the product of the momentum with the speed of light squared plus the rest mass times the speed of light squared. And we use this little mnemonic triangle to help us remember the relationships between these quantities. It looks like a Pythagorean triple where this side is m naught c squared. That represents the rest energy. And this is the contribution of the momentum times the speed of light. And on this side, the length of that side of the triangle then becomes the total energy of this particle or object under consideration. So this squared plus this squared equals that squared. And if you want to think about it, if you rotate this base around, you can divide the energy up into a part that is a contribution from the rest mass, and then another contribution that we would call the kinetic energy. That is the contribution from motion. Okay, so that was where I ended at the end of last lecture, but I never explained where this formula comes from. So let's just spend a couple of minutes going through a derivation of where this formula comes from. And what we're going to do is we're going to start out with three formulas. The first formula is E equals mc squared. That's the foundational formula for the relationship between energy and mass. And keep in mind that the mass, what we really mean is the rest mass times the gamma factor times c squared. That's the first formula that we're going to appeal to. The second formula was just the formula for this gamma factor, 1 minus v squared over c squared, and the inverse of that. And the third formula is the formula for relativistic momentum, which is mass times velocity, or if we wanted to write this in terms of the gamma factor, gamma times the rest mass times the velocity. So what we're going to do is we're going to combine these three formula, and we're going to end up with this formula right here. So how do we do that? Well, first of all, let's use equation 2. Let's square this and reorganize it a bit. So we're going to square both sides. 1 minus v squared over c squared, and then we're going to multiply both sides by the denominator, and when we do that we get 1 minus v squared over c squared, and then we'll divide both sides by gamma squared, so 1 over gamma squared like this. And then if we can solve for v squared over c squared, which we can, we get v squared over c squared equals 1 minus 1 over gamma squared. Okay, so we're just going to keep this in mind. We're going to put that in our back pocket, so to speak. We'll come back to that formula later. We basically just solved this definition. We've solved this definition for the quantity v squared over c squared. All right, now we're going to use equation 3. Equation 3, the first thing we're going to do is multiply it by both sides by c and then square both sides. So on the left side, we'll have p times c squared. On the right-hand side, we'll have gamma squared, m naught squared, c squared, v squared, like this. And then what we're going to do is, with this formula, we're going to multiply the top and bottom by c squared. You'll see why I'm doing this in a moment. So we'll have gamma squared c to the 4th times m naught squared times v squared over c squared. But we already know v squared over c squared is 1 minus 1 over gamma squared. So there's just some algebra here. And now we recognize that gamma squared m naught squared c to the 4th, well, that is just the energy squared. That's what all this stuff becomes using equation 1. Right? And then we're left with 1 minus 1 over gamma squared still. And then let's multiply through. We have e squared minus e squared over gamma squared. And remember, e squared over gamma squared is just going to be m naught squared, oops, go back a second, m naught c squared squared. Okay, where we have used equation 1 once again, using equation 1 once again. And so we're left with pc squared equals e squared minus m naught c squared squared. And then we can solve this for the energy, e squared, and we arrive at the formula that we're trying to arrive at, m naught c squared squared, which is what we wanted to arrive at. Okay, and so then let me just say one other thing about this formula. You can think about what the total energy of an object is as a function of its momentum. And you can see that when the momentum is 0, it still has some energy, and that energy is m naught c squared. So if we set p equals 0 in this formula to the square root of both sides, we'll see that the energy is minimally m naught c squared. That's the rest energy, or the energy associated with it, with its resting state. And then what happens when you go to very high momentum? This term, the first term on the right-hand side, dominates. The second term gets very, very small. So what happens when this term dominates? We get e squared equals pc squared, or in other words, the energy is directly proportional to the momentum. So way up here at high momenta, you'll have a linear relationship between energy and momentum. So it's going to look like this, and it's going to have a slope is going to be equal to the speed of light. So somehow, as the momentum increases, it goes from this value up to a linear relationship between energy and momentum. Okay. All right, and let me see if there's anything else I wanted to say about this. Maybe I'll say one last thing. Notice that in this formula, if an object has no rest mass, so for example, for a photon, we'll come back to this maybe in another class when we do our introduction to modern physics. For a photon, the rest mass is equal to 0. That's the particle of light. And in that case, we have just the energy is equal to the momentum times the speed of light. All right, so that's the case for a 0 rest mass object. That's the relationship between energy and momentum. So there you would have a linear relationship all the way up like this. Oops, it should go through 0. Sorry, I made the slope not quite right, but you get the point. It goes like this, and the slope is c all the way. So the fact that it has mass changes this from a linear relationship like E equals p times c to something that asymptotically approaches m naught c squared. Okay, I hope you have enjoyed my lectures on Einstein's theory of relativity. It's been a very cursory or quick overview. We went through a lot in a very short amount of time, and so I hope you have the chance to study this again sometime.